Hello, class. Welcome to our combinatorics lecture for Monday, April the 13th. Sorry I'm late getting this lecture posted because I'm preoccupied grading, as you know, and I may be late also on posting Wednesday's lecture, so that may not show up until Thursday, um, um, April 16th instead of Wednesday, April 15th. Because I'd like to try to get your test returned to you by Wednesday. Um, so we have been talking about inclusion and exclusion, and we're going to continue with some advanced examples of inclusion exclusion today before we're finished with that. Um, and I will have homework ready for inclusion exclusion. So that should be posted sometime on Monday as well, later on Monday. I've got that ready, but I just haven't posted that yet. So again, and so that's the next homework that will be due. I haven't chosen the due date for that. Um, Probably that will be um, in a week or so um, to turn in. Okay, so we're through with the test. Thanks to everyone for turning in the test, and we do have one more test scheduled that will be at the end of the semester, which is really approaching quickly, right? Things are moving fast, so that will be at the end of this month. In a couple of weeks will be the last test, and then I'm hoping that many of you will have the option of not taking the final exam and replacing that by the average of your test scores. But for others of you who will want to take the final exam to improve your test scores, you can check the calendar to see when that final exam is scheduled. But we'll be conducting the remaining exams like we did this by email, like we did this past exam that seemed to have gone smoothly. Um, Okay, so I've got, again, a couple more examples of inclusion-exclusion that I want to look at today, more advanced examples. But the first thing I have to do is I have to correct a mistake, or actually a couple of mistakes from examples that I gave you last time. So I'm not going to completely repeat the examples, but I want to show you where the mistake that I made, and it's corrected in the note. So I'll repost the note. See, this is why I need to. It's so difficult to record these lectures because I don't have you guys sitting in front of me, and you could help me catch these mistakes before I've gone too far. Right? Everyone is doing combinatorics problems. It's easy to overlook subtleties or easy to make mistakes. That's just the nature of the subject. Okay, so we were doing a problem last time. This problem number 3 of inclusion exclusion. So the statement of the problem was you wanted to find. So if you watch the video for the videos for last week, you'll recognize this example. We wanted to find the number of integers between 1 and 1200 exclusive that are divisible by 5 or 6 or 8. Any one of these three numbers. So, so we can solve this problem by inclusion-exclusion in the following way. What we were going to do is let A be the set of these integers that was divisible by 5, and let B be the set divisible by 6, and let C be the set divisible by 8. And so if we take the union of those three sets, A, B, and C, you will recall, of course, that would be integers divisible by 5 or 6 or 8. That's exactly the set that we're asked to count here, right? So this is a perfect situation for inclusion-exclusion. We are trying to find the cardinality of the union, right, of these three sets. So we just applied our inclusion-exclusion formula, right, to compute the cardinality of the union of those three sets. And, of course, we saw it was going to be the sum of the cardinalities of the three sets, right? This is the typical inclusion-exclusion pattern, right? So we would include the cardinalities of the three individual sets, right? And then we have to exclude, right, or subtract off the cardinalities of each of the intersections of a pair of the sets. So we were going to subtract off the cardinality of A intersect B, the cardinality of A intersect C, and the cardinality of B intersect C. Those are the three possible pairwise intersections you could form from these three sets. And then we would include, so we would add back in, right? It's that inclusion-exclusion pattern, right? So then we would add back in the cardinality of the intersection of all three sets, right? So the intersection of A and B and C, all right? And so then we went about trying to count these individual cardinalities. So we counted the integers, the elements of the set A, right? That's integers divisible by 5, and then we counted integers divisible by 6, and then integers divisible by 8. That integers between 1 and 1200 divisible by 5 or 6 or 8. And those were pretty easy to count. We ended up with, I think it was 240 plus 200 plus 150. This one turned out to be 240. This one turned out to be 200. This turns out to be 150. Okay, and then we set about trying to count the cardinalities of the intersections, right? So this we had to think about more carefully. So we were thinking about what this intersection means, A intersect B, and that would be integers divisible by both 5 and 6, right? Integers divisible by both 5 and 6. And we said, well, integers divisible by both 5 and 6, that means they would have to be divisible by the product of 5 and 6, which is 30. And so how many integers between 1 and 1200 are divisible by 30? Well, that's easy. It's just every 30th integer, correct? So we took 1200 and divided by 30, and that gave us 40, right? Okay, so that's correct. All right. So so the size of this set is 40. And the size of this set, we use the same reasoning for A intersect C. The size of that set turned out to be 30, okay? And then this is where I made the mistake, all right? So trying to compute the cardinality of B intersect C. That would be integers divisible by both 6 and 8, okay? Integers divisible by both 6 and 8. So I was trying to be too fast here, and I said, well, integers divisible by both 6 and 8. That means they would have to be divisible by the product of 6 and 8, which is 48, right? Okay, and so I just took 1200 divided by 48 and got whatever that number was, 25. Okay, so I said, oh, the size of this set is 25. All right, down here. But that's a mistake, all right, because what I really should have done is figure out what is not just take the product of 6 and 8, which is 48, that was correct, but what I should have done here to determine integers divisible by both 6 and 8, I should have looked at the least common multiple of 6 and 8. And the least common multiple of 6 and 8 is not 48. It's 24, okay? The 6 and 8 both divide into 24. So integers divisible by 6 and 8 means that that's every integer that's divisible by 24, not 48. So it turns out that there's twice as many elements of this set as I originally thought, okay? So integers divisible by both 6 and 8, that would be integers divisible by the least common multiple of 6 and 8, which is 24. So to count this set properly, I should have taken 1200 divided by 24, and that turns out to be 50, okay? All right, that turns out to be 50. And then I made the same mistake with counting the size of this intersection, A and B and C. That would be integers divisible by 5 and 6 and 8. And I said, well, that's the product of 5 and 6 and 8, which I think was something like 240. But again, that's incorrect. What I should have said was to find integers divisible by 5 and 6 and 8, that means integers divisible by the least common multiple of 5 and 6 and 8, which is not the product of 5 and 6 and 8. Yeah, it turns out to be 120. When you compute the least common multiple of 5 and 6 and 8, you get 120. So integers divisible by 120 are divisible by 5 and 6 and 8. And so that's the least common multiple. So if you take 1200 and divide it by 120, you get 10 instead of, I think before I had only 5 in this set, but actually it turns out there are 10 elements in this set. And so then when I insert these new values here for the sizes of these intersections, I end up here with a different sum. So I end up with 380. So it turns out there are 380 integers between 1 and 1200 that are divisible by 5 or 6 or 8. Okay, so the 24 here is not the size of B intersects C. That's the least common multiple of 6 and 8, which is 24, and the least common multiple of 5 and 6 and 8, which is 120. And so then when you take 1200 divided by 24, you get 50, and then when you take 1200 divided by 120 instead of what I did last time, which was 240, I get 10. So so the correct totals here were the sum of these three sets, which is 590, then minus 40, minus 30, minus 50. Last time I had 25, but minus 50, and then plus 10 instead of last time I had plus 5. And that comes out to be a final answer of 380. All right, so you will have problems like this one, number 3, in your homework, and so pay attention to this correction that I made. And I made the same mistake a little bit. We had a very similar example a little bit further down here, a little bit more complicated example. I was trying to find integers between 1 and 1200 again that were divisible by 5 or 6 or 8 or 10. And so so I defined 4 sets then instead of the 3 sets in that previous example. And then again we used inclusion-exclusion to find the size of the union of those 4 sets, right? So here's my inclusion-exclusion computation. And again, I made the mistake when I was trying to compute the sizes of these intersections. I made the mistake of not looking at the least common multiple. For instance, look at this last intersection that you have to subtract off. That's the intersection of all 4 of the sets. So before I was thinking, okay, the intersection of these 4 sets, that would be integers divisible by 5 and 6 and 8 and 10. And I said, well, that means the integers would have to be divisible by the product of these 4 numbers, which is a very large value. And so I thought, oh, well, there are no integers between 1 and 1200 that are divisible by the product of these 4 values, right? And so I thought this intersection was 0. But, of course, that's not correct, right? Integers divisible by 5 and 6 and 8 and 10 means integers divisible by the least common multiple of these 4 numbers. And the least common multiple of these 4 numbers is not the product of these 4 numbers. It's actually 120 is the least common multiple of 5, 6, 8, and 10. So to calculate integers between 1 and 1200 divisible by all 4 numbers, just take 1200 divided by 120, right? And you end up with, instead of 0 here, you end up with 10. So there were several instances in this example where I made that same mistake, right? When I was trying to compute the sizes of these intersections, instead of looking at, I was looking at the product of numbers instead of the least common multiple of the numbers. So I had to go back and recalculate the sizes of these intersections. So here I fixed them in my calculations. And the final answer turns out to be different than what I had before. It turns out to be 380. I think last time I had maybe 370, but it turns out to be slightly larger. Okay, so the correct answer, I think the correct answer to this last example, number 4, from the last notes is 380. So be careful of that complication when you're doing problems in the like this. In the homework number 6, which I mentioned already, I'm going to post soon, right? Okay, well, so sorry for that confusion, but again, that's just the nature of combinatorics, right? These subtleties sometimes catch up with us, and sometimes we have to go back and you know and reconsider our solutions. So well, I have a couple of more examples today. So let's see if I let's see if I can get through those without making mistakes. But if not, well, I'll just have to, in the next video, go back and fix those mistakes. All right, so let me close this. Let me close these notes, and let's look at notes for today. Okay, so let me scroll up here. I'm a little bit below where I want to be. Oh, all right. Okay, so this is just another a direct application of inclusion and exclusion. Okay, and it involves more than 3 sets. So it's going to be a this is going to be kind of an advanced example, and it has lots of calculations in it. But the calculations themselves are simple. Okay, so it's the calculations are not difficult. There's just a lot of them. So this is a lengthy example, but it's not a particularly difficult example. It's just long. Okay. All right. So let's read the problem here. So we have a sock. All right. This is kind of not an unusual setting for a combinatorics problem. A sock filled with marbles. Okay. Often combinatorics problems are stated like this. You have a drawer filled with socks, or a sock filled with marbles, or lots of situations like this. So here we have a sock that contains some marbles, all right, and 3 red marbles, and 4 blue marbles, and 5 green marbles, and 2 clear marbles, right? And what we're going to do is just blindly pick 10 marbles out of the, oops, I said drawer there. So we're going to pick 10 marbles from our sock, right? And so we want to know how many color combinations are there, right? Okay. So keep in mind that marbles tend to look alike, right? So these are not numbered marbles, but so the only way we can distinguish one marble from the next is by the color of the marble, right? Okay. That's it. So the 3 red marbles, as far as we're concerned, are all really the same. And the 4 blue marbles are all the same, and the 4 green and the 2 clear, right? Okay, so be careful about, as always in combinatorics, right, if you're dealing with distinguishable or indistinguishable objects, because that really changes the answers to questions. All right, so but you get the idea, right? You know, again, how many color combinations are there? So, for instance, you could get one combination would be 3 red, 4 blue, right? 2 green and 1 clear, because that adds up to 10 marbles. Or you could have no reds when you make your, you know, when you blindly choose the 10 marbles out of the sock. You could have 0 reds, 4 blues, 5 greens, and 1 clear marble, right? Okay. Again, that's a different color combination, right? Okay, so so here's how we're going to think of the problem. All right, I'm going to transform this to a different problem, but one that you are familiar with and that you already know how to solve. So this transformation is from kind of a marble problem to a different setting, to a different kind of problem, is just to make the problem more familiar to us, transform it into a problem that we already know how to work, okay, or almost already know how to work. All right, so here's the way I make that transformation. I'm just going to choose some variables here, x1 through x4, and those variables are going to represent the number of marbles of particular colors that I draw, right, when I draw the 10 marbles. So we're going to let x1 be the number of red marbles chosen. All right, that's really the only way we can really distinguish the marbles, right, is by the number of color, the number of marbles of each color that we choose anyway, correct? Because remember, the individual marbles themselves are not distinguishable except by their color, right? So I'm going to let x1 be the number of red marbles chosen, and then we're going to define similar variables for blue, green, and clear. So x2 will be the number of blue marbles, x3 will be the number of green marbles that I choose, right, when I choose 10, and then x4 will be the number of clear marbles that are chosen. So notice here that as soon as you defined x1 through x4, then this becomes an algebra problem, because if you add up x1 plus x2 plus x3 plus x4, right, you get this nice equation, because you know those four values must add up to 10, right? Okay, because you've chosen 10 marbles out of the sock, right? Okay, so you get this equation, and of course, then what you're interested in is, well, how many solutions then are there to this equation? So we have a question about the number of integer solutions to an equation, right? Which we are well familiar with how to solve this problem that was on the last test, correct? So see, we've changed this this marble problem right now into this more familiar type of problem for us, right? Which is just how many solutions are there, how many integer solutions are there to an equation. However, there is one complicating factor in this equation. We don't have an unlimited number of each color marble, right? So this x1 cannot be as large as we would like, or the x2 cannot be as large as we would like, right? Or x3 or x4, because we only have a certain number of each color of marble. So we have to write down those restrictions. So notice x1 has to be between 0 and 3, because we only have 3 red marbles. And x2 has to be between 0 and 4, because we only have 4, blue marbles, right? And x3 has to be between 0 and 5, because we only have 5 green marbles. And then likewise x4, right, has to be between 0 and 2, because we only have 2 clear marbles. So we do want to find the number of integer solutions to this equation, but we've got restrictions. And we've dealt with finding solutions to an equation with restrictions before, but not quite restrictions like this, okay? So these restrictions are a little bit different than what we worked with in the past, right? Okay, all right, so, but let me show you how we're going to handle these restrictions, all right? So, so here's what I'm going to do, okay? We're going to treat this as a complement problem, okay? So look, first, let's look at solutions to this equation, same equation, right? But without these upper bounds on our variables, okay? So let's just take off the restrictions at first, that x1 is less than or equal to 3, x2 is less than or equal to 4, x3 is less than or equal to 5, and x4 is less than or equal to 2. So let's just remove those restrictions, those upper bounds for the time being, and just consider the solutions to the same equation, but just where my variables are non-negative. So all my variables are bigger than or equal to 0. So of course, if you drop these restrictions and just look at the solutions to the equation without these upper bound restrictions, then you're going to have a lot more solutions, right? Okay. So the set of solutions to the equation without the upper bound restrictions, okay, that's going to be a much bigger set of solutions than with the upper bound restrictions, right? So I'm going to think of that set of all solutions without the restrictions as being my universal set, and I'm going to call that set S. So let's let S be the set of all solutions to this equation where we drop the upper bound restrictions. And we know how to count that set, right? Okay, because that's a very now familiar problem to us. So remember, you're going to transform that into a problem involving strings of characters, right? So I'm not going to go through that process because you're all familiar with that from the second test. But it turns out that if you repeat that process, so you can do that yourself and see that the size of S here, the number of solutions to the equation without the upper bound restrictions, is going to be this multinomial coefficient, 13 choose 10 comma 3. Which, when you compute that, is 13 factorial over 10 factorial times 3 factorial, And when you simplify those calculations, you just get 286. So it turns out that, so you can see how to do those calculations. They're pretty easy arithmetic. So you get 286. So if you look at all solutions to the equation without the upper bound restrictions, just that x1 through x4 has to be bigger than or equal to 0, right? Then there are 286 solutions to that equation. So that's a lot more, right, than the answer to our question, because we're interested in solutions where we have these upper bounds, right? But if you just look at all solutions without the upper bounds, you get there are 286 of them. All right, now, how am I going to reduce that 286 to the solutions just that I'm interested in, right? The solutions that have these upper bound restrictions on them. Well, here's what I'm going to do. I'm going to define 4 sets here, all right? So I'm going to let A1 be the solutions out of S, right? So out of all the solutions, let A1 be that subset of solutions where x1 is bigger than or equal to 4, where x1 is not less than or equal to 3, but bigger than or equal to 4, okay? All right, and then, so hang on, you'll see where I'm going in a second. And then I'm going to let A2 be solutions where x2 is, out of all possible solutions, the solutions where x2 is bigger than or equal to 5. Okay? And then I'm going to let A3 be solutions where x3 is bigger than or equal to 6. And then let's let A4 be solutions where x4 is bigger than or equal to 3. All right? So notice these restrictions seem to be opposite of the restrictions that I really have in the problem, correct? Okay. But how do these sets help me then with my original problem? Well, I want you to observe here very carefully. If you take the complement of A1, that would be solutions where x1 is less than 4, right? In other words, where x1 is less than or equal to 3, right? x1 is less than or equal to 3. That's the complement of A1. And the complement of A2, well, that would be solutions where x2 is less than 5. That means less than or equal to 4, correct? And the complement of A3 would be solutions where x3 is less than 6, not bigger than or equal to 6, but less than 6. That means that x3 is less than or equal to 5, right? Okay, and if you look at the complement of A4, that would be solutions where x4 is less than or equal to, well, less than 3, which means less than or equal to 2, correct? Right? Now, so we know what the complement of A1 is, we know what the complement of A2 is, we know what the complement of A3 is and what the complement of A4 is. Notice if you take the intersection of these 4 complements, right? If you take the intersection of these 4 complements, then what you have is solutions where x1 is less than or equal to 3 and x2 is less than or equal to 4 and x3 is less than or equal to 5 and x4 is less than or equal to 2. That's exactly the solutions that you're looking for, right? Okay, that's exactly what we wanted. So the intersection of these 4 complements, that's why I set up these sets like I did, the intersection of these 4 complements is exactly the set that we were interested in finding. See, so notice what I have here is, wow, this is going all the way back to the beginning of the class, right? I have a set model now, right, for my for the set that I'm interested in counting, right? It's the intersection of these 4 sets, right? Okay, but I know how to count the intersection of these 4 complement sets, right? Because remember, this would be the same as the intersection of the complement, right? Okay, I'm sorry, the intersection of the 4 complements is the same as, writing it up here, that's the same as the complement of the union of these 4 sets, right? That's just elementary set theory, correct? The intersection of these 4 complements is the complement of the union of these four sets. But how do I count the complement of any set? I take that set, right, okay, and I subtract it from my universal set, which in this situation, right, I take the cardinality of this set and I subtract it from the cardinality of my universal set. But I know what my universal set is, right? That's the set of all solutions to this equation without any restrictions. I already counted that. That's 286. And now, how do I count, though, the union of the four sets, correct, right? The complement of the union would be the universal set minus the cardinality of the union, correct? How do I count the cardinality of the union? That is inclusion-exclusion, right? So what we've done is transform this problem, strangely enough, right, into an inclusion-exclusion problem, right? All I have to do is calculate this, the cardinality of this union, right, and subtract that from the cardinality of my universal set, and voila, right, I will have the answer to my question. Okay, now look, we're only about halfway through this problem, right? Okay, because now we have to apply inclusion, exclusion. Wow, that was a fun transformation, though, right? So we, again, we transformed that sock full of marbles problems, right, into a problem involving integer solutions to an equation, and that, and then with restrictions, though, right, integer solutions to an equation with restrictions, and then I had to transform that into an inclusion-exclusion problem, okay, which we are now ready to solve. All right, so let's see, what is the size of this union, correct? Remember, I'm subtracting it, so all the signs are going to get reversed, right? So what do? First, you take the sizes of the individual sets, right? A1, A2, A3, A4, right? Okay. Normally, right, you would be adding those first, right? If you were computing the size of this union, but since I'm subtracting, I'm going to subtract all of those first, right, from the universal set, and then we will. Now, here's where the signs alternate, right? Now we will add back in, okay, the the size of the intersections of each pair of sets, right? So I have to take each pair of sets and compute their cardinalities. I'm sorry, take their intersections of each pair of sets and then compute the cardinality of those intersections, right? So let's see how many of those intersections will there be. How many pairs of sets are there that we have to intersect? Well, you've got four sets altogether, right? And to intersect two of them, you have to choose two of the four sets, right? To intersect them, that number is 4 choose 2, which turns out to be 6. Did I write down? So I should have 6 pairwise intersections here. Well, do I have them all written down? Let's see. A1 intersect A2, A1 intersect A3, A1 intersect A4, A2 intersect A3, A2 intersect A4, and then A3 intersect A4. Yeah, there's 6 of them, right? So there's all of the pairwise intersections, correct? Remember, normally I would be subtracting off these pairwise intersections, right? But since I'm subtracting this cardinality of this union, right, from the universal set, these become plus. So now I'm adding in the cardinality of these pairwise intersections. Now, what do you subtract off, right? See, it's always alternating signs, right? So now what do we subtract off? Well, we have to subtract off the cardinalities of the intersections of 3 of the sets, triples, right? Okay. So first individual sets, and then pairs, and then triples, and then we'll go up to quadruples here, right? Last. How many triples are there that we have to intersect? Well, we've got 4 sets altogether, and a triple, it consists of 3 of them, right? So how many ways can I choose 3 sets from 4? How many ways can I choose 3 objects from 4? That's 4 choose 3. That turns out to be 4. So I should have 4 triple intersections here. Is that what I've got? Do I have them all written down? I think so. A1 intersect A2 intersect A3, A1 intersect A2 intersect A4, A1 intersect A3 intersect A4, and then finally A2, A3, and A4 intersected. So I have to find the cardinalities of those four sets. Hopefully I can do that, right? Okay. And then we have to add back in now, because we're, again, switching between including and excluding, right? So now I have to add back in the cardinality of four of them intersected at a time. Well, there's only four sets to start with, right? So if you choose four of them, that's all four of those sets. A1 intersect A2 intersect A3 intersect A4. So I've got to figure out what the cardinality of this intersection is, right, and add that back in. So if I can compute all of those, I don't know how many different numbers there are there, right, that I have to calculate. If I can calculate the cardinalities of all those intersections, add them and subtract them, right, according to this formula, once I'm done, I will have my answer, right? Okay, I will have the intersection of the complements of the four sets, and that's exactly the set that I wanted to count. All right, so now we have to go about the business of counting all of these cardinalities, right? So the only one that we know so far is S. Remember, that was 286, right? So I can fill that in, but now I've got to fill in what's the size of A1, what's the size of A2, what's the size of A3, and so forth. All right, so I've done these calculations now already, so let me explain these calculations to you, okay? So what about the size of A1? So what does A1 mean again? Remember, what was that set? How do we define that? That's solutions to that equation, right? x1 plus x2 plus x3 plus x4 equals 10. But I only want solutions where x1 is bigger than or equal to 4. But you've solved problems like this now, again, on test 2, right, where you have restrictions like this on solutions to an equation, right? So if I want x1 to be bigger than or equal to 4, and the sum of all four of my variables has to add up to 10, then what we can do is think of go ahead and assign 4 units to x1, right? And then if you go ahead and just immediately assign 4 units to x1, then that means when you add up your variables, they're really going to add up to 6, right? Because you've already pre-assigned 4 units to x1, right? Since x1 has to be bigger than or equal to 4, right? And you had 10 units that you were assigning to start with, right? So 4 of the units have been assigned. So the cardinality of A1 is really just the solutions to this equation, where x1 plus x2 plus x3 plus x4 is 6, right? Since we already know that we want x1 to be bigger than or equal to 4. All right, but how many solutions are there to this equation then? That's easy, right? Okay, you can just count the solutions to this equation without any restrictions. Well, other than that the variables are non-negative. Okay, and so you did that on the test again, right? So that turns out to be easily C. That's 9. That's this multinomial coefficient 9, choose 6, comma 3. When you do these calculations, you get 84. So the size of A1 turns out to be 84. So we can go ahead and add that into our computations here, right? Okay, so see, by making this transformation of this problem, although I have lots of cardinalities to compute, I have the tools, right, the knowledge to compute, I hope, these cardinalities. And the first one we have calculated, well, the first two actually we've already calculated, right? So so we have a lot of computations to do, but it's computations that we know how to do, right? Okay, it's things that we already know how to do. All right, so what about A2? Well, you can use exactly the same logic here. A2 would be, that's solutions where x2 is greater than or equal to 5. So you can think of going ahead and assigning 5 units to x2. So you would get the equation x1 plus x2 plus x3 plus x4 equals 5. Because of the 10 units, you've already assigned 5 to x2, right? So now when you add up your 4 variables, they only add up to 5 because we've already assigned 5 to x2, right? If you count the solutions to this equation, it ends up being this multinomial coefficient, 8, choose 5, comma 3, and that, when you calculate it, turns out to be 56. So the cardinality of A2 here is 56. So using exactly the same logic, you can compute the cardinality of A3. That turns out to be 35. And the cardinality of A4, that turns out to be 120. So just try calculating those. So we get minus 35 and minus 120 for this top line here in my inclusion-exclusion formula. All right, now what about A1 intersect A2? What's that cardinality? Okay, well, let's think about it. A1 let's scroll up here to the definition of my sets. A1 intersect A2. So A1 was solutions where x1 is greater than or equal to 4. A2, solutions where x2 is greater than or equal to 5. So if you intersect those two sets, you get, right, solutions where both of these things are true, right? X1 is bigger than or equal to 4, and X2 is bigger than or equal to 5, right? Okay, so how many solutions to that equation, right, do we have where x1 is bigger than or equal to 4 and x2 is bigger than or equal to 5? Not many, right? Okay, that would be essentially pre-assigning 4 units to 1 of the 10, right, and 5 units to x2, right? Okay, so that means 9 units have already been pre-assigned to these two variables, so you've only got 1 unit left to work with, right? So, so the size of this set is really, the size of this intersection is really just the same as the solutions to this equation, x1 plus x2 plus x3 plus x4 equals 1. And that's very easy to see. That's going to be 4. So the size of this intersection is just 4. So now we add back in 4. Cool, right? Well, again, now we can use the same logic to find the size of A1 intersect A3 or A1 intersect A4, etc. What about A1 intersect A3? That means that x1 has to be bigger than or equal to 4, and x3 has to be bigger than or equal to 6. Well, remember, these 4 things only add up to 10. So if x1 is already 4 and x3 is already 6, I think there's only one solution to that equation, right? Okay. So there you have it. A1 intersect A3 is 1. Wow, okay. What about A1 intersect A4? That means x1 is bigger than or equal to 4, and x4 is bigger than or equal to 3. That turns out to be a number of solutions is 20. And for A2 intersect A3, this one is nice, okay? A2 intersect A3, that means x2 is bigger than or equal to 5 and x3 is bigger than or equal to 6. But that already adds up to 11, but the equation can only be 10, right? In the equation, your variables can only add up to 10. So the number of solutions here is 0. For A2 intersect A4, then we end up with 10 solutions, and for A3 intersect A4, we end up with 4 solutions. So, so there's what we add back in. So I have plus 4, plus 1, plus 20, plus 0, plus 10, plus 4. Now, what do we subtract off? Well, now we have to calculate the intersection of 3 of the sets. These turn out to be all easy to compute. Let's take an example. What about A1 intersect A2 intersect A3? That means that A1 intersect A2 intersect A3. That means that x1 has to be bigger than or equal to 4, and x2 has to be bigger than or equal to 5, and x3 has to be bigger than or equal to 6. But add those together, and that's already 15. But remember, your variables can only add up to 10, right? So notice that this intersection is 0 because you can't have solutions, right, where the variables meet the conditions and still add up to 10. So this intersection is 0. And actually, it turns out that all of the triple intersections are all 0. You can't have any solutions that meet these conditions on the variables. And likewise, the intersection of all 4 of the sets also has to be 0. So there you have it, okay? Not really that difficult to calculate all those cardinalities, although there's a lot of them. Not really difficult to compute all of them. When you add all these together, when you add all these numbers together, by the way, you just get 30. So there is there's the answer to the original question. Came out kind of low, but that's it, right? So there it is. There are 30 ways of 30 different combinations of the 4 colors when we choose 10 marbles from that sock. Okay. Wow, neat. That's a really nice example, and really demonstrates here the power of inclusion exclusion. Okay, because that's a hard counting problem, I think, without inclusion exclusion. Well, but very similar, and this one's show you next time how to do this problem, though I'm not going to go through this example because these examples are kind of lengthy, right? And so we're going to eat up all of our time doing examples. But so we'll look at this one next time quickly. Okay, it's very similar to the prior example. It's just stated in a different setting. I think if you look at this one yourself, you can figure out how to set up this problem. Okay. Now I do want to show you though one more thing today, and this is the subject called derangements. Okay. And so we're going to learn how to count derangements, which is a particular type of permutation. But again, we're going to use inclusion exclusion to count again derangements, which is a particular type of permutation. So here's where inclusion exclusion we can apply to help us count permutations. We've been counting permutations almost since the beginning of the course, right? Okay, but we're going to show how inclusion exclusion can apply to count certain types of permutations. Let's take let's pause here though for a moment, okay, before we come back and look at this application of inclusion exclusion, if I can get my recorder here to respond. Okay, so as I mentioned before the pause there, we're going to learn how to count now using inclusion exclusion. We're going to develop a theory for counting a particular type of permutation that's called a derangement. And you'll see very clearly where the term derangement comes from. So suppose you have an integer segment bracket in, right? So remember, integer segment means, from the very beginning of the course, right? That is that would be the set of integers up to, starting at 1, going up to a particular positive integer, right? So the integer segment n is 1, 2, 3, right, up to the integer n, correct? But we want to consider permutations then of this set, right? But where no number is in its correct position. So, so again, a derangement is a permutation of integer segment, but where in the permutation none of your integers end up in their correct numerical position. So let's take an example just to make this clear if it's not clear. So let's look at the integer segment 4. That's a simple integer segment, right? So remember 4 there. Brackets 4 there is going to be this set 1, 2, 3, and 4, and so of course there are lots of permutations, right, of the 4 integers in this set, but we're interested in counting permutations where none of these numbers end up in its correct numerical position. So there ends up being 9 possible derangements of this set, and here they are all listed out. Okay, so so here's just one of them, 2, 1, 4, 3. So that's a permutation, right? That's just an arrangement of the numbers in this set. But again, notice that no number is in its correct position, right? 2 is in position 1, 1 is in position 2, so those aren't in the right spot. 4 is in position 3, and 3 is in position 4, right? So see, no number is in its correct numerical position, so that's why this is considered a derangement. Or 4, 3, 2, 1, right? You can see, right, that again, no number is in its correct numerical position, right? So this also is considered a derangement. So what we're trying to develop here in Theorem 10 is just a formula for counting the number of derangements of an integer segment, and then we can apply that to finding derangements of other sets as well, correct? Other sets of objects as well. All right, so well, here's the statement of the theorem, and so it's a really interesting formula, but and easy to apply. But what's really cool about this formula for derangements is how it comes about. It's going to come about through inclusion and exclusion. So it's really one of the key applications of the idea of inclusion exclusion, right? So do you understand how the formula works? So we're going to let dn be, that's going to be my notation for the set of derangements of an integer segment. So this is a set now. And so if we want to find the cardinality of this set of derangements, then here's the formula. So it's just going to be n factorial. That's probably not a surprise, right? Because derangements are a particular type of permutations, right? And we know they're n factorial permutations of this integer segment n. But then we have to take the n factorial and we have to multiply it by this kind of complicated factor here. And you can see where inclusion and exclusion reveals itself, right, in this formula. So so here are the terms inside the brackets that you multiply by n factorial. You'll take, easy to remember, you take 1 over 0 factorial minus 1 over 1 factorial plus, notice the signs are alternating, 1 over 2 factorial minus 1 over 3 factorial plus, etc., up to, and then, of course, whatever the final sign ends up being here, times 1 over n factorial, right? Okay. By the way, notice the way the signs alternate. There's a very easy to remember pattern there. When the factorials are of positive numbers, so when the factorials in the denominator, are of even numbers, then the sign is going to be positive. But when you have 4 factorials of odd numbers in these denominators, the sign is going to be negative. So 0 is an even number, so it's plus, right? But 1 is an odd number, so this we subtract. 2 is an even number, so we add. 3 is an odd number, so we subtract, and so on and so forth. Okay, in that alternating pattern. All right, well, but before we're going to prove this theorem. Again, it comes from inclusion and exclusion, but before we prove it, let's just apply it in one simple example here. Let's notice a moment ago we counted, just because we listed them all out, we said that the size of d sub 4, that is the derangements of the integer segment 4, was 9. Let's see how that comes from this formula, right? So according to the formula, to find the cardinality of D4, we would take 4 factorial, right, times, and then this big factor inside the bracket. So it's 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial up to plus, in this case, 1 over 4 factorial. Stop at 4 factorial, right, since we're finding the derangements of the integer segment 4. Okay, well, what does this reduce to? Miraculously, it's going to reduce to an integer. Okay, well, let's see what integer that would be. So let's go ahead and take the 4 factorial and multiply it by every term here inside the brackets, because there's not that many terms inside the brackets. So I get 4 factorial in the numerator, right, of all of these fractions. And then these things are all going to reduce easily, right? By the way, 4 factorial is 24. when you compute it. And 0 factorial is by definition 1. So this first fraction is 24. And then you have 4 factorial over, well, 1 factorial is 1 again, right? So you have a 24 over 1, which is 24 again, which you're subtracting. And now 4 factorial over 2 factorial, well, that ends up being 4 times 3, which is 12. And then you have 4 factorial over 3 factorial, that turns out being 4. And then 4 factorial over 4 factorial, of course, that is going to be 1, correct? So you get this big sum and add that together, and you're going to see that turns out to be 9. All right, so that agrees, of course, with what we stated earlier for the number of derangements of the integer segment 4. Okay, now let's see, where does this big complicated formula come from? All right, so as I promised you, it's going to come from inclusion and exclusion, right? Okay, so here's our proof of that formula. So we're gonna use complements here. So we're gonna use the complement version of inclusion exclusion. So what I'm going to do is take my universal set as the set of all permutations, not just the derangements, right? But the set of all permutations of the integer segment n. That's going to be my universal set. And what I'm going to do is subtract off from the universal set permutations that are not derangements, okay? So I'm going to take all permutations and then subtract off permutations that are not derangements. And then, of course, what I'll be left with are the derangements, okay? So that's the general scheme here to derive this formula that I showed you in Theorem 10. So I have here as universal set all permutations of the integer segment n. Of course, you know there are n factorial of those, right? So that we've known since very early in the semester. All right, now, how am I going to set up my complement? Well, here's what I'm going to do. I'm going to define several sets here, okay? So let's let A sub 1 be all the permutations where 1 is in the first position. So notice that is not a derangement, right? Okay, if 1 is in the first position, permutations like that are not derangements, okay? Because remember, a derangement, you want every number in not to be in its correct position, right? So permutations where 1 is in the first position, that's not a derangement. Then let's at A2 be permutations where 2 is in the second position. Again, not a derangement. And let's at A3 be permutations where 3 is in the third position. So those sorts of permutations, not derangements, right? And then finally up to A sub n, I'm going to let that be permutations where n, the last number, is in the last position, right, where it should be, or where its natural position anyway. I don't know if it should be there, but its natural position. So again, notice this is permutations in A sub n are not derangements, right? Okay. Now let's look at the complement of all of these sets that I just defined. So first, let's just describe those complements, right? So if A1 is permutations where 1 is in the first position, then what's the complement of A1? That's where 1 is not in the first position, right? What's the complement of A2? That's permutations where 2 is not in the second position, right? Okay. A sub 3 complement, that would be permutations where 3 is not in the third position. And so on and so forth up to what's A sub n complement. That's permutations where the last number, n, is not in the last position, right? So I want you to notice here, what happens if you take the intersection of all of these complements? Well, what do you get? You get A1 not in the first position. I'm sorry, you get 1 not in the first position. You get 2 not in the second position. You get 3 not in the third position. You get 4 not in the fourth position. 5 not in the fifth position, etc. up to last number not in the last position. All right? So the intersection of all of these complements would be essentially what? No number, right? 1, 2, 3, 4, all the way up to n, no number would be in its correct position. in the intersection of these complements. That is a derangement though, right? Okay, so the set of derangements is the intersection of the complements of those n sets that I defined. But this set, right, we know how to count using inclusion, exclusion, right? It's the intersection of a bunch of complements, so that means it's the complement of the union, and I know how to count the union using inclusion, exclusion. And so if I subtract that union from the universal set, I will have the complement. Well, here it is. Okay, so this is Theorem 9 back from the previous notes. Here's how you, according to inclusion, exclusion, right? Here's how you count the intersection of a bunch of complements. It's the universal set minus the sum of the individual cardinalities plus the sum of the pairwise intersections minus the sum of the triple intersections plus the sum of the quadruple intersections. Then you would be what? Minus the sum of intersections taken 5 at a time, right? Plus the sum of intersections taken 6 at a time, minus, etc., right? Up to finally, and this could be plus or minus depending on how many of these sets you originally have, right? Finally, the last thing is the intersection of all of the sets, correct? I've got the wrong subscript here. This should be in. Okay, so minus or plus, depending on how many terms we end up having in this sum, right? The intersection of the cardinality of the intersection of all of the sets, right? That's just inclusion, exclusion. Okay, so let's see if we can apply this formula in this particular situation, right? So in this computation, I know what my universal set is, right? That's the set of all permutations, right? So I know already that is in factorial. See, so you can already fill in to this calculation in factorial, correct, right? Okay, because you know that. That's great. So we're, one tiny step there along the way, right, of doing these computations. Now, what about each one of the individual sets? What's the size of each of the individual sets? All right, so let's see if we can analyze that, right? What is this sum, adding up the cardinalities of each of the individual sets going to be, right? Okay. Well, let's remember how those sets were defined, right? Remember, in general, right, the set A sub I, that was going to be the set of permutations where integer I is in the correct position. So integer I is in position I, right? Integer I is in position I. So all the other integers, right, might be mixed up, but integer I is in position I. Okay, so how many permutations have that characteristic? Integer I is in position I. Well, how many integers were we arranging? There were n of them, correct, right? But one of them is in the correct position, so you put it I in its correct position, and then that leaves you n minus 1, right, remaining integers that can be in any order. They can be in any of the other positions, right? The remainder, which is n minus 1, can be in any of the other positions. So look, that means you can take the n minus 1 remaining and you could put them in any arrangement that you like. And how many ways can you arrange n minus 1 integers? It's n minus 1 factorial. So if you look at permutations where I is in the correct position, there are n minus 1 factorial of those. Well, that's just one of the sets, right? Okay, but we have n of these sets, so the sum of the cardinalities of all of these would be n, because there are n of them, times n minus 1 factorial, because each set has size n minus 1 factorial, right? So you get n times n minus 1 factorial, but that just simplifies to n factorial. Ooh, okay, right. So now, we can fill this in, right? This big sum here, all of this is just n factorial. Well, that's cool. So you have n factorial minus n factorial to start with. Notice these two things cancel each other. You start with 0. Okay, now what's next? We have to look at the pairwise intersections, right? A sub I intersect A sub j. What's the size of that? And then remember, there's a lot of those, correct, right? And then we have to add all of those together. This also is easy to analyze, though. You can use really the same logic, right? So here it is. What about A sub I intersect A sub j, right? Okay. Well, just look in general at A sub I intersect A sub j. A sub I intersect A sub j. That means that we had permutations where I is in the correct position and j is in the correct position, correct? So two of your integers are in the correct positions, right? Okay, but the other remaining integers could be all mixed up. Well, how many such permutations are there? Well, just go ahead and put I and j in their correct position, and then how many integers do you have left to mix up? Well, that would be n minus 2, right? So you put 2 in their correct position, so you have n minus 2 left that you can arrange any way. How many ways can you arrange n minus 2 integers? 2 of them are correct, right? But how many ways can you arrange the other n minus 2 around the 2 that are correct? Well, that's n minus 2 factorial, right? That's how many ways you can arrange n minus 2 objects as n minus 2 factorial. So each one of these pairwise intersections has a cardinality n minus 2 factorial. But how many of these pairwise intersections are there? Well, how many ways can you choose 2 of these subsets out of the n of these subsets, right? Choose 2 to intersect out of the n subsets. It's n choose 2, right? So you have n choose 2 of these. Each one of them is this large. So when you add all these intersections together, you get n choose 2 times n minus 2 factorial. If you do those calculations, here I've done them for you, that reduces to this number, n factorial over 2 factorial. So there's another term we can add into our list here. This is n factorial over 2 factorial. Nice, right? Now we go on here, right? Okay. How big is each intersection of 3 of the sets, right? How big is each intersection of 3 of the sets? And then add all of those possible triple intersections together. All right, well, look, you can use, again, still the same logic, okay? So if you've got A1 intersect AJ intersect AK, that means what? Integer I is in the correct position. Integer j is in the correct position. Integer k is in the correct position, right? So these integers are all in their correct positions. What about the other integers? They can be all mixed up, though, okay, around these 3 that are in the correct position. Well, so how many, if you've got 3 in the correct position, that means there are n minus 3 that can be rearranged. How many ways can you rearrange n minus 3 integers? It's n minus 3 factorial, right? Okay, so each of these sets is n minus 3 factorial large. Each one of these intersections of 3 of these subsets is n minus 3 factorial. But how many of these subsets are there, right? Well, how many ways can you choose 3 subsets to intersect? That's choosing 3 sets out of the n sets, so you get n choose 3. So when you add up all of these intersections of triples, you get n choose 3 times n minus 3 factorial. And when you do that calculation, it simplifies again nicely. It's just n factorial over 3 factorial. Oh, well, look, so I think now, let's fill that in. But I think now the, let me see if I can fill that in back up here. Wow, I'm going to have to scroll a lot here. There we go. So this is n factorial over 3 factorial. I think now you can see the pattern. So we had n factorial minus n factorial plus n factorial over 2 factorial minus n factorial over 3 factorial. You can already guess what this is going to come out to be. Using exactly the same logic as before, this turns out to be n factorial over 4 factorial. And so forth. This one turns out to be, not surprisingly, the last one, n factorial over n factorial, which, by the way, is 1, right? So there we have it. Let's fill those calculations all in. Here's my formula again that I was trying to count all these intersections, right? Let's fill in what we know. N factorial minus n factorial plus n factorial over 2 factorial minus n factorial over 3 factorial plus n factorial over 4 factorial, etc. Here down to this last term would be n factorial over n factorial. Looks like I just repeated my calculations there. But now what I'm going to do is factor out n factorial from each of the numerators here, right? In this, see, notice in this big sum, each one of these fractions, I see. The n factorial over n factorial, the n factorial minus n factorial, I wrote that as n factorial over 0 factorial, and then n factorial over 1 factorial, just to make a consistent pattern in these fractions. And then from each one of these fractions, I am going to factor out the numerator, which is n factorial. And so that leaves you with this formula there, and that's the formula that we wanted to prove, right? So there finally is the number of derangements of the integer segment, and it's n factorial times this big quantity inside the brackets. Miraculously, that always turns out to be an integer. It looks like it's going to be a fraction sometimes, but it doesn't. It always turns out to be an integer. All right, let me check our time here. And because want to do one more example where we actually apply this formula now that we've gone through all of that work to derive it. Let me see if I can get my recorder to respond. Here it comes. Okay, all right, so let's pause there. We have just enough time to do one example. Okay, so let's finish here with just one application of our derangement formula. So let's look at this problem. We have 6 married couples. I'm going to try to be gender neutral here, but we have 6 married couples come to a dance. And in how many ways can the couples mix dance partners so that no person dances with their own spouse? Okay, so so how many such arrangements are there of the 6 married couples, right, into new couples, right, so that no one, for dancing purposes, so that no one dances with their own spouse? All right, so here's an easy way to think of the problem, right? Let's, as they walk in the door, think of numbering both halves of the couple, right, okay, with numbers. So a couple come in, both partners would be labeled 1, right? And then the second couple comes in, both partners would be labeled 2. Third couple, both partners are labeled 3, right? And so on and so forth, right? Until we have labeled both partners in all 6 couples, right? Now, of course, we don't want each partner, right, to dance with their own spouse, correct? So what we want to do is rearrange one half of each couple, right, so that that's the case, right? So, for instance, we could here match like this, right? Person 1 from the first couple, right, with person 6 from the person 1 from the couple 1, right, with person 2 from couple 6, correct, right? This is person 1 in each couple, right, and this these numbers represent person 2 in each couple, right? So and then so on, right? We could mix person 1 from the second couple with person 2 from the 5th couple, right? And so on and so forth, right? So these dance partners, right, would meet this. These dance partners, right, would meet this criteria, correct? That no person is dancing with their own spouse. But look, this is just one possible way, right, of mixing up the couples, correct? There's a lot more. And how many, right, can we do that? Well, notice what we've written here in this third line to form these dance partners. This is really just a derangement, right, of the integer segment 6, correct? Okay, and every time you write a new derangement, right, of the integer segment 6, you're going to get another way of creating dance partners, right, where no person is dancing with their own spouse. So what we're really asking here is for how many derangements there are of 6 objects, right? Or in particular, how many derangements are there of an integer segment 6? So what we're really trying to count here is just the cardinality of D6, right? That is the answer to this. That's the answer to this question. So again, now we can apply our nice formula to this, right? So we know from theorem 10, right, that this is going to be 6 factorial times 1 over 0 factorial minus 1 over 1 factorial, right, plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial, right? And so if we can do these calculations, then we'll have the answer to this question. So I'm not going to do the calculations now because we're out of time, but this turns out to be, when you do these computations, you get 265. So the answer to the question is 265. Okay, so that's all the time we have for today. So remember, again, Wednesday's lecture might be late, okay, like today's lecture was, and because I'm grading tests. But I hope to have those tests back to you by Wednesday. As soon as I have those, I will post them. The grades, I will post those grades in Blackboard and email you, but also and then return the test to you by email, right? Okay. All right. So I will see you guys later this week. Okay. Stay safe as always. Wear your face mask when you're outside, right? Wash your hands. Okay. We don't want anybody expiring on us here when we're so close to the end of the semester. All right. So take care.